Either one works for me, Sid, just as long as it's consistent.
Okay. Folks, I'd recommend everyone to please use the chat box. It is just an interface that everyone's familiar with. And we'll keep track of that chat box for questions. Thanks.
Thank you, Sid. Please help me out wherever. Sorry we didn't coordinate on this beforehand. Okay, welcome everybody to a webinar on APIs for liquid cooling. We have two speakers today. Jeff Autor from HPE. Jeff has been leading the Redfish and API thrust for a decade or so. And Ryan Grant. Ryan is from Queen's University, and Ryan's been leading the PowerAPI for, Ryan, how long has it been? 7 years?
Yeah, 7, 8 years. Yeah.
Yeah. So both of them are very seasoned, and their APIs extend way beyond just liquid cooling. Today, we'll give you a brief overview of the entire, what is the API that they're working on? How do they interact? And then dive down a little bit into the liquid cooling section. And then you'll be invited to participate more broadly or more specifically in their specification efforts. So with that brief introduction, I'm going to turn the floor over to Jeff. He's going to have a little less than a half hour to talk, and we're going to leave about 5 minutes at the end for questions. Okay, Jeff, take it away.
Great, thanks, Natalie. Hi, folks. Good morning, good evening. For anyone that hasn't heard this talks before, I'll try to be brief and get through all these this prepared pieces. So, as Natalie said, my name is Jeff Autor. I'm with Hewlett Packard Enterprise. I also co-chair the Redfish Forum in the DMTF standards organization. I'm also involved with the Open Compute project and the hardware management group there, as well as obviously with Natalie's group with the EEHPC. So with that, let me get into the Redfish for liquid cooling equipment. So as Natalie said, Redfish has been around for coming up on a decade now. We extended the specification in the data model into the data center infrastructure space back in 2019. That started with models for power distribution equipment, specifically rack PDUs and floor PDUs. Further extending into the liquid cooling space, and that all of the material I'm showing today was released right about a year ago now, back in early May of 2023, and that was part of the Redfish release bundle called 2023.1. So the extensions here benefit the industry in a couple ways, specifically for both the producers and the consumers of this data. So on the client side, since you're using the same protocol and the same data model for all kinds of equipment in the data center, Redfish started in the server management space and moved into storage. A little bits of networking here and there, but the data center equipment was really the last frontier to kind of make sure that everything in the data center could be covered. So by using that single data model, a lot of that what I'd like to call the housekeeping function. So whether that's updating firmware, doing security to security management and certificates, setting up events, event destinations, and all of that ilk. All of those functions are the same across all the devices. So you don't have to do a lot of it, vendor specific tools for things like firmware update, which we know is a huge consumes a lot of time and effort on the part of the administrator. So that's the first thing. And the second thing is that the actual all of the supporting functions around physical and logical associations, all of these things, these are all consistent across the various pieces of equipment. So once you understand the model, all you're learning when you hit a new piece of equipment is really the subject matter for that piece of equipment. So, obviously liquid cooling has a lot of very unique pieces, but all the rest of it is all just, very common stuff. So, and that also benefits the folks implementing these things because, since there are client tools for all those housekeeping functions, that means they don't need to produce their own tools and models for that stuff. And so again, they get a lot of engineering efficiency and can take advantage of that whole ecosystem. So my goal with all of this is to get us out of the re-implementing management and management protocol pieces over and over and over again as we go from piece of equipment and generation to generation, and we never get to the more interesting upstack things that all of these equipment should be able to do, and that's things like measure and allocate for better efficiency, reduce energy consumption, and for sustainability, and et cetera, et cetera. So the goal, my goal is like, let's get out of re-implementing the same basic stuff over and over again, and move on to the more interesting things that I think everyone would like to get to. But as I've said, the last slide there, before you can do any of that, you have to be able to measure and monitor everything first. So that's kind of where we were at with the Redfish models. So let me get into the actual models themselves. So trying to be generic and cover as much equipment as we can. So some of these names may be very very generic, but we're trying to make sure that it will make sense in the future. So all the cooling pieces are all under what's called the thermal equipment model. Redfish being a REST interface, everything's driven by URIs. Everything at Redfish starts at a discoverable service route. There's a new property here called thermal equipment that gives a link to one new section of the tree. In all the Redfish terms, things under service route are generally links and just used for discovery. Once you understand the model and know the equipment you're talking to, you don't have to follow all these things. You can go directly to the stable URIs. So the new thermal equipment resource is located off of the service route. I've got a picture here coming up, and then it allows for the attachment of one or more pieces of cooling equipment that are sorted into various collections of like gear. So this could be a proxy that is managing many cooling distribution units. It really depends on the system architecture. So it could be one or more of any of these things. So we have divvied up the equipment that we know of and support directly so far. Things like CDUs, immersion cooling units, or immersion cooling tanks, also freestanding heat exchangers, and cooling loops that may be managed or just need to have a home in the model for folks to be able to chase all the connectors around. So the tree looks like this. As a user, again, this is hypermedia based. So you start at the service route, and that's at Redfish v1. There are generally two links that come through any piece of equipment. There's what I like to call the functional, which you may want to call the logical model, but I try to avoid that term. The functional model is thermal equipment, and so you can see here there's a room you could have the heat exchangers and immersion units, CDUs, and cooling loops. The other part of the model is the physical model, and that's almost exclusively under what's called a chassis, which is really just the Redfish term for some kind of box. So every CDU will have a chassis that contains all that gear, and then there are links here between that make the bridge between the physical and the functional views. So let me get into the individual pieces. This is where the meat of the model gets to, and you'll actually get to see some payloads here. So let me start with the cooling loop. The cooling loop is trying to describe the physical connections, between various pieces of gear. And so there are two parts to this. There is the cooling loop itself, and that's that could be nothing more than a pipe. And so it's really, from our perspective, it may just be a complete software construct. There may not be anything truly monitored at the cooling loop itself. But we need that in the data model so that so you can chase the connectors around. The bulk of the management and the readings that can be obtained through the model is all at the connector, because that is the interface and where the measurements usually take place. So in Redfish, this is called a coolant connector. And so you make a connection between a cooling loop and some piece of equipment. And so the connector can be, and obviously these are since these are generally loops, so there can be a supply and a return side. Those can be monitored or rendered as individual connectors depending on on the needs of the gear. But we also allow a connector to effectively render as a pair of connectors, so that you get both a supply and return in one resource. And so whether the flow or the temperature measurements are on the intake or the output side, or both, that can all be gathered at once, and you can that way can more easily correlate, and you don't have to get overly complicated if that's not necessary. And I'm all for not trying to make things more complicated than they need to be. And I said, I'm going to go through this quickly. And by the way, these slides I'll show you, give you a link to where they're available. So, and obviously we'll get them through Natalie's mailing list as well. So here's an example, just a very simple block diagram of what the model looks like. So in this case, I've got a physical rack that's containing a bunch of gear. In this case, there's a primary side, facility water system cooling loop, and then there's a secondary or technology cooling system, or if I get that acronym right. There's a loop that comes out of that through the CDU, and then that is in feeding individual servers. So each of the blue arrows here represents a coolant connector in the Redfish model, and so this can all be rendered from the CDU's perspective. So depending on where those measurements are taken, those may show up under the CDU's tree, or if it's the piece of gear, in this case their servers, if they have their own interfaces and sensors, they can be correlated because the connectors allow them to be named and allow you to chase those through the whole system here. So following the coolant flow, you have a connector coming from this cooling loop. It goes to this CDU. There's a connector from the CDU output to the technology loop, and then another connector or set of connectors to each of the individual servers. And so all of that can be discovered if everything is fully implemented, and then measurements are shown at each of these connection points. And just scaling this up, this could be many pieces of gear, and could be separate management interfaces that again we want you to be able to correlate those links and be able to show how the liquid is flowing around the data center, hopefully all within the pipes. So in this case I've zoomed out here, so here's that same kind of CDU picture of an individual rack. In this case there's two racks here that are both connected to this primary cooling loop at the chiller level of the data center. So in this case, this CDU doesn't really have any direct information or knowledge about where it's coming from. It just knows that it's connected to the to the outside world from its perspective, and so that's why there is the ability in the model to manually name, just provide effectively strings that explain where those connections go, so that if programmatically you can't chase those links, at least the humans can be informed of where those connections are, so so that messages and status can be chased down. So here, let me get in now to that's kind of the block diagrams. Let me get into to show you some examples of what each of these resources look like and the kind of data that you can get. So starting with the cooling loop. So as in Redfish, there's because you can have one to many of most of these pieces. So almost everything in Redfish shows up as a collection of these resources. So a cooling loop connection has one or more cooling loops. And as I showed in the first slide, this is linked from the thermal equipment model and resource. So the cooling loop reports generally, the product information, location, and capacities, ratings, and so forth. There's a place in there for describing the coolant that's contained within the loop. So a number of pieces there. It depending on on how much information the system wants to allow you to store. But again, this is mostly for discovery, and then for service and maintenance personnel to be able to access and track. There are the ability to have some metrics at the cooling loop, so things like the coolant quality and coolant levels. Those are available. And then as I said, several ways to represent the connections and name them. That can be could be just a list of names of equipment. If it's not something that doesn't have a Redfish interface or is otherwise just not managed, and so on both the supply and the consumer side of those, upstream, downstream, lots of ways to describe the flow of the coolant through the system, and then lastly, if there are things like existing GUI interfaces or other APIs. We have the ability to go list those URIs out so that folks using the Redfish interface can discover the like, okay, well, I may not have a lot of information about this piece of gear, but let me give you a link to the to a URI that where another management interface exists. So here's an example. So this in Redfish, this is all in JSON. So a get on this resource, and this is exactly what you will see on the wire, and then in your client or web browser or whatever you're using to access this. And so you can see here, here's that coolant. So this is showing that this is a water-based loop with a little bit of biocide added in. But it is water. It could be a fluorocarbon or hydrocarbon-based coolants. There's enumerations for those. You can see that the status of the coolant is okay, and it's reading a normal quality level. And then here's some examples of those of all those equipment links where I have. Here's on the supply side, it's connected to a chiller, and on the consuming side, I'm connected to 4 different racks. And then here are the links to the collection of connectors on both the primary and the secondary side, and like I said, that's where the meat of the model comes in, and so I'll get into that here in a second. So on the other side of the equipment is the cooling unit. This is the generic name for any piece of cooling equipment gear. So that this one schema, because it's all very, very similar. They all have make, model, and serial number. They all have connections on a primary and a second or a secondary side. A bunch of sensor connections and monitors and so forth. So we use one schema to describe all of that kind of gear. And then subdivide them in the model so that if you're looking for immersion tanks, you can find those more easily. And then every resource has a very generic type property that would describe the kind of gear that you're looking at. And I'll show you what that looks like. Again, trying to leverage the model as much as possible, but we don't want to get ridiculous. So at least in the cooling units, everything we've modeled so far. All had 90-something% shared terminology and property information. So we were able to do that. So as in most of these equipment type of static resources, this resource has a lot of the general product information, make, model, and serial number, hardware revisions, data manufacturer, and then a link. And then links to a lot of subordinate resources that provide all of the various subsystems. So when I click here, you're going to see a big exploded diagram, and it's not as bad as it looks. So where we had started before, we were chasing up the service route, came down. So I'm coming here through a one CDU. So this is a collection of CDUs. So here's the one particular, and you can see there's a bunch of subsystems here. A lot of the larger and more complicated units may have more than one of these things. So we have collections of reservoirs and pumps and filters. And like I said before, the meat of the model is all handled at the connector side. So you'll see a bunch of this stuff. So in the interest of time, I'm going to kind of go quickly through these. The mock-ups and all this material, of course, is available. So again, cooling unit resource so you can see here, the kind of the typical inventory pieces. And then I've collapsed it here because there's a lot of hypermedia links to all of those monitored subsystems, and that's what I want to get to. And as I've said before, the coolant connector is where all the monitoring happens. So I want to show what that resource looks like. So I've truncated here because it won't fit on the page, but again, here is as you saw, same names and definitions on the cooling loop. The coolant is here as well, and then showing some of the rated pieces for the connector. And then you get a lot of, and I've only got room on here for a couple. I should have shown more. But pressure readings, temperature, and flow rate are all available in this one resource. So one will get you all of the readings for that single connector or pair of connectors. So you'll see that the names here follow the supply and return terminology. So you're seeing here, I'm getting the temperature and the pressure on the supply side, and I also have delta temperature, delta reading. So that you'll see that on temperature and pressure. Obviously, flow rate has to be had better be a constant there. I'm going to skip over, but one of the areas of interest, especially for the Open Compute project, was rear door heat exchangers, and so this is just a diagram showing how one of those heat exchanger units fit into the model. Because we already had a lot of the air cooling pieces monitored and modeled under the chassis and computer system models. So we leveraged all of that, and so that is where all of that equipment shows up. And it only renders itself as actually a piece of cooling equipment, if it is either contains or part of a CDU. Otherwise, this is done with could be an external CDU that has a very small cooling loop that connects just to the heat exchanger. And as I said, there's a bunch of subsystems. So I'll just show these very well. Actually, I'm not going to show those at all. But like I said, there are the resources will look very familiar by this point. A lot of the same make, model, and serial number kinds of information for things if they are freestanding units, or if they're just subsystems, they may have less information because it would just be repetitive. And then you can there'll be some of the obvious things. Pumps have pump speed. Filters have service time and install dates and so forth, and filter types. Again, trying to help folks be able to discover both runtime monitoring and also kind of service and maintenance information in general. So I'll close on our leak detection. This was an area that did extend the Redfish model in some other ways. We had started trying to do these discrete value types of sensors, and that just gets really bogged down into a whole area that we didn't want to get into. So we came up with a I think is a better answer, and so we've explicitly defined a leak detection in a subsystem. So leak detection is a huge topic for all the liquid cooling folks. So we did take quite a bit of care on this topic. So the leak detection subsystem has its own resource that describes the various detectors available and how they are grouped together. And you can have both leak and humidity based pieces. So and then at this point, the policy as to what happens or how when is something declared a leak, that is left to implementation. So we're certainly looking for feedback on that as to see what else can we provide and explain to that. But when a leak is detected, then it follows the standard and common status definitions for all Redfish resources. So I'll show you one piece here. So this is an actual detector. I'm sorry, this is the leak detection piece, and so there is a group. You can have more than one leak detector groups. So this particular group says this is the detectors, under and around the CDU, and that detector group has a humidity reading, And then it has 2 individual, detector or leak sensors. And both of those are luckily, hey, are both showing okay. So if they're not okay, they would show a detector state of alert, and that's basically how that works. And if that was the case, you'd also see that information bubble up to the top level conditions. So yeah,
Thanks. Great, perfect.
yeah, I was right there with you. So so please, if you're a vendor building cooling equipment, the models are available. There's a white paper, there are tools for validation. All of these things are available. We are getting a lot of interest from some of the key vendors, and I know there are implementations in flight. So I have not seen anything in the wild yet. Intel showed some pieces at Supercompute last year. Mohan, and I think familiar to folks here, has shown some examples of this. So I'm looking forward to seeing folks actually being able to utilize this and have it have it show up and be useful to the folks trying to manage all their data centers. So again, all this information is available. Natalie's been great for allowing us to talk here. Once again, the place to go here before you write all this stuff down is just go to redfish.dmtf.org. That's the developer portal, and links to everything that the DMTF produces on this front is all available from there.
All right, actually, we have 1 minute. So there are 2 questions and a couple of questions in the chat. Why don't you go ahead and choose one of them, and then I'm going to turn the floor over to Ryan, and we'll carry the questions to the end.
Okay, let's see. Is there a recommended mechanism, Redfish fields, to query the entire system to discover all the connections and mappings between the racks and the cooling units and the servers? There was a relevant section. The first, is there a more direct way to just query for specific info? So the way that Redfish works, it is a REST interface. It is based on HTTP. So you get what we did was try to flatten the model as much as possible. So we divide those resources up, as I showed, where you get a lot of information, with one get, and then you shouldn't have to be doing those over and over again. So you get one resource and get many pieces of data, and then we keep those resources small when there's a lot of changing information, metrics, and so forth. So you'll see it's a fairly flat model, and so you don't need to query individually for 1 or 2 pieces of data. You'll get all of the links, for instance, from one piece of equipment and the list of connectors. Those individual connectors are individual resources. So once you kind of start drilling down and following your links, then you're not pulling lots of extraneous data. You are gonna get just the stuff you need, but you absolutely can follow the links and discover the entire tree and follow that all the way through the data center. So, and I'll leave the rest of these for the remaining time. Thanks.
Thank you, Jeff. Okay, Ryan, please tell us about PowerAPI, and then at the end, we'll have some time for questions.
Great, happy to. Jeff, do you mind unsharing? Thanks. Great. Get on to PowerAPI. Okay, hi everybody. I'm Ryan Grant. I'm speaking about PowerAPI today. I've been chair of PowerAPI for a while, but PowerAPI has been around a fair length of time. Natalie, we mentioned right before the recording started that PowerAPI, I've been doing it for 7 or 8 years. It's actually been the first issue came out in 2014, so it's been 10 years, believe it or not. All right, everybody. So PowerAPI is a standardized interface for power and energy monitoring and control. We're software only, so I'll draw some parallels and differences here with Redfish as well, in terms of you could use Redfish inside of a PowerAPI wrapper if you wanted to as well. But that's not the only way you can use the PowerAPI. So first of all, before I explain the cooling control section of the PowerAPI, I really need to explain what the PowerAPI is to make sure everybody's on the same page. Otherwise, it would be very confusing. So the PowerAPI really is meant to be comprehensive system software as a portability layer to interface with power measurement and control hardware. So we don't care whether that hardware is speaking something that's Redfish We don't care if that hardware is speaking something that is vendor proprietary. We use a plugin infrastructure in our reference implementation to provide multiple different drivers into multiple different pieces of hardware with a single unified software interface amongst them all. So you can think about us as in a type of abstraction layer with a whole bunch of bonuses and extra things included in it that we can do that make your life easier. The goal here is that the Power API is meant to be comprehensive across many different levels of a data center, both in terms of the users and their privilege levels and what they're trying to do on the system, as well as the equipment that's available. And that works with both individual platforms inside that data center, as well as facility-wide equipment too. So what really happens in Power API is that we have many different actors that can interface with a single API to perform several different roles inside the system. And the system is logically organized into objects in our object hierarchy. This means that we encompass everything from facility level concerns down to low level hardware software interfaces. We are a binary interface, so I'm not going to be able to show you cool JSON like Jeff did earlier, but that means that we are still a set get type interface, but that we're meant to do so very rapidly. So you can gather collections on items of interest, attributes we call them, inside of an object very quickly with the Power API. So first, I'm going to touch on just the actors for a second. This has less to do with our cooling controls, but you have to understand sort of the scope of the overall Power API before it will make sense. So there are many different roles, and where you see these orange triangular shaped boxes, those are probably people, right? Yeah, facility manager is a person, and they're interacting with systems that are either the high performance computing system manager, the facility hardware, resource managers, monitoring control systems, operating systems, hardware independently as well. And so many different actors, there are many different entrance points. For example, you might have a user who's dealing directly with resource manager. What does this mean? Kubernetes, Slurm, whatever your independent resource manager for allocating resources on the system is, the user's interacting with that group. The HPC admin is dealing with many different items throughout the system, but we might also have somebody who's just doing accounting. All they want to do is come in and look at your overall, for example, power consumption over the last several months. So we want to encompass everything from a user needing user and admin needing very fine-grained power measurements off of the system for energy measurements, in addition to fine-grained setting of attributes, for example, power states and things like that, that you need to happen very rapidly, as well as long-term statistical data that we gather about the system as well. So there, as you can imagine, there are multiple moving parts underneath this one API to be able to provide two different services, one which is very rapid access, very quick turnaround time, and one which is more historical access that's going to go back to storage systems and gather and crunch data for you over long periods of time. So how do we express a system? So that's how those are the usage models for what we wanted to use, but how do we actually express this programmatically so that you can look through a system and understand what objects are available? Those will be pieces of system hardware typically, and what capabilities they have, what attributes we can query on them, and we can get a whole bunch of metadata about these individual items as well. Now, this is a very simplified version of the Power API system model. It's directly from our specification. And you can see that basically the idea is that we have a platform. We have a facility above the platform. This is what's currently in the standard, but we've actually added the facility now so that we can support multiple platforms. We have a platform, but let's just think about that as a single large system, right? In there, we have cabinets, or you can think about these as racks. Right? Inside there, we might have a board, right, that may contain multiple nodes. In the past, we did have larger boards that multiple independent CPUs clicked into, for instance. But you might also think of these as a rack and then blades within that rack. That can blade chassis that controls many of those. Then you have a node. That's what we would typically think of as a computer, right? It has its own operating system. It might have several CPUs attached to it or GPUs, but that is a node. That's how we're defining node. And then we have a socket. And a socket is something that you can think about that as a CPU socket if you want to. And then underneath that, each independent socket, that would be a physical CPU chip, for example, would have a computational core. There's a lot more to this, but that's the basic system model. And these are things that we guarantee exist so that you can programmatically move through the system. There may be no concept of a board, for instance, in this system. So when you ask for the child of a cabinet, you may get many nodes instead of independent boards. But we guarantee that some of these objects exist in this particular order. There are a whole bunch of objects that we allow that do not have to happen in this order, but programmatically, this makes it a lot easier to try to move through the system, because all you're doing is going from parents or from parents to children. So you can generate, you can discover what children a given item object has, and you can go to its children directly, or you could go up to your parent. So you navigate up and down this basic hierarchy with a whole bunch of components. Now here's an extended system model view that gives you an example of a single cabinet with a chassis, has some boards, has some nodes, sockets. They have something called power planes underneath them, which just let us group together like things that have consumption of power, and cores underneath. So I point out that things like accelerators, network interfaces, memories, all these sort of things can exist. They're not tied to this specific defined hierarchy. So there's no rules about that where it needs to show up, and that will be key for us understanding how we do our CDI work our CDU work in the future. Okay. So why do we even have these objects? Well, it's much easier to explore a system programmatically. So like I said before, we're navigating up to parent objects and down to child objects so that we can very easily iterate through these large trees, discovering more about the system as a whole. And each of these objects then has a set of attributes that allow you to get and set certain attributes to monitor and control things. So you could think about getting an attribute from a node, for instance, that is power. You could also get that attribute from a GPU or a core, or I could get that attribute from an entire chassis or an entire rack. The Power API will return to you the sum of all the objects underneath the larger object in that whole. You can query things like temperatures, power states, set up things like power caps, frequencies the devices are working at, all sorts of things that you can set there as well. And there's rich metadata here for you to understand these things as well. So you can understand how a measurement is taken, what frequency it's actually being used internally, even though that might not be exposed to you externally. So for example, a piece of hardware might be sampling at 30 kilohertz internally, but only exposing that result at 100 hertz. And so metadata will tell you all of these things. Are we holding chat till the end, Natalie, or do you want me to touch on them now? I can just hold it to the
That's up to you, Ryan. But I do want to hold 5 minutes for mutual questions.
Okay, great. I'm just seeing the chat explode, but it looks like it's mostly Jeff. I just want to make sure I was answering everybody's questions. So why do we want the Power API? When we've got things like Redfish, why do we need a Power API? And the answer to that is really, it's a portable standard for power monitoring and control with both out-of-band and in-band measurements that's independent of the underlying hardware standards that might be imposed. So for example, you might want to run this on your system that has Redfish capabilities in it. You might also want to run this system. I'll give you an example. Power API, Fujitsu developed an implementation of Power API for the Fugaku supercomputer, which is a great little implementation of, well, not little implementation, it's a great implementation of it. And that lets us use a single interface to programmatically change things and monitor things on all of these systems, regardless of who the vendor is and what standards that they're adhering to, because we can always support it via plugins underneath. So this really lets you write code once and use with many different vendors. We can write things like power optimization tools that are truly portable, regardless of who we're buying from, unless the world goes to one overarching dominant standard. This is a really useful thing for us to do. And it gives us a binary level interface in C. So we can do low overhead, rapid measurement and control of items throughout this system too. Oh, there we go. So what have we been doing in liquid cooling controls? Now that you've been introduced to the Power API, the basics there, what are we doing from the liquid cooling controls? There's an element of the Power API that I haven't introduced yet that I wanted to introduce here called group functionality. You may create arbitrary groups of objects within the Power API. And this means that we can use groups for understanding how things are connected and the interdependencies of things in liquid cooling controls as well. I've got some figures of this that I'll show you graphically in future slides. And in the Power API, many groups can exist at once, containing potentially overlapping objects, which helps us with redundancy systems as well. So the idea is that we're going to build groups of hardware served by cooling units. We're going to add in cooling units as an object as well, so we can understand things in many different ways. And we're going to build groups of that hardware with dependencies for certain cooling infrastructure where it exists. So the goal here is to support a large variety of liquid cooling setups in a portable way. So before we get to the groups exactly, let's talk first about the attributes that we've had to add for liquid cooling controls. Now, I'm not talking here about things that would be included in the metadata interface. These would be things like what your coolant type is and all that sort of stuff is not a direct attribute. It's information about the system. It's not something that we're actively setting and getting. I don't know of a system where I can actively change the coolant type on the fly, so it's not something I need to programmatically control. That would be part of the metadata, for instance. So we have things that taken from a EHPC working group report on liquid cooling, their liquid cooling focus group that came up with some of these items, which I'm borrowing from them here to give you an example of some of the attributes. So things like water flow, both from a system perspective as well as from CDU perspectives. You can also look at water flows where sensors exist inside of objects. So you could think about the water flow into a node, for instance, if you have a sensor there. We already have thermal data in the system, so you can figure out temperatures of pretty much everything and have them all aggregated together for you, or drill down to individual components and gather those items portably as well. We already have power. And we know how to do this quite well. I should mention that the Power API really specializes in aggregating data for you. So if you want to know the power of an entire system, that's okay. We have overlay networks that do that reduction for you in a really efficient way throughout your system, so that you're not clogging your network with too much traffic, or you're flooding a single management node that has to do all of that math because everything's delivered directly to it. We do things smartly in reductions with overlay networks. So we can do things like collect an entire system power in a low overhead manner because we can do the reduction for you. We also have things like dew point temperature, pump speeds where pumps exists, pressure differentials, valve positions, this sort of stuff. We attach these things to the most logical object next to said valves. So if you have valves going into every single node in a rack, you can set your valves on a per node basis. If you have a valve into a rack, you can set that there as well as get information about how it's working as well. So how do we combine together this idea that we have these new CDU objects that we've added, in addition to the attributes that are available on all of our objects with regards to liquid cooling, and our groups? So how do all these three concepts sort of come together? So you can see now that before we had a facility item, hopefully people can see my laser pointer here. The facility item is the entire facility. We have a couple different platforms here and a couple different approaches to how you can create a CDU group. So these are little big cooling groups. For example, in this one, we have racks, and this CDU is basically sitting next to some racks. And within this one rack, there's a chassis and there's some nodes that this CDU happens to serve. The CDU can also serve another rack. So this is a grouping of objects underneath this particular item that where a single CDU is serving it. We also have an idea where they're a little bit more hierarchical, where a CDU could serve as multiple racks and how these things happen. But the point that I want people to take from this is that the CDU itself is not a strict element of that hierarchy. It can fit in wherever it needs to fit in. So let's look at some reasons on why we want that and how things can be useful to us. So we can also understand CDUs in terms of their overall placement, and we can also group CDUs together. So now I can understand that underneath my platform, I might have some CDUs here, regardless of whether they're an in-rack CDU or whether it's a CDU that services an entire row. We don't care. What we can do is we can also create dependency groups between these by creating groups in the Power API. So in this case, you can see we have this first green group that says CDU 0, 1, and 2 can essentially cool the same things, right? And CDU 1, 2, and 3 have some overlap as well. So if we lost, for instance, CDU 1, right, I could potentially be using CDU 2, which would otherwise not be used. Let's just say that CDU 0 and 1 are the normal cooling group for a set amount of hardware underneath it. And CDU 2 and 3 are the normal cooling group for a set amount of hardware underneath it. But if I lost CDU 1 or CDU 2, I could use the leftover capacity from CDU 2 to come over and cool some of this hardware. Or if I lost CDU 1, I could use some of that to come over and cool part of this hardware. So overlapping redundancy is important because we also need to support with PowerAPI very, very large systems where these types of CDU interdependencies happen. And it's really useful to know, do you really need to shut down all the equipment that's sitting underneath here if we have a CDU failure, or can we absorb that into the rest of our system as a whole? So the idea here is that we can group not only objects like we had here with CDUs. Hey, here's a CDU and here's all the stuff it possibly can cool or is cooling, right? We can also use the same functionality to group CDUs with information about that group to tell us what that is. Now you might say, how do I end up with a group? And the answer is, for groups like these and for CDU interdependencies, your individual implementation can provide those groups from time t=0 when you initialize the PowerAPI interface. So there will be some groups that exist for you that are provided, things like these cooling groups, so you can understand how the system works as a whole. You can, of course, read tons of metadata in this system as well to fully understand what the ramifications of these groups are and why they're grouped the way they are. In addition to this, we have groupings of CDUs that would be provided as well, but you can also manage to group these things entirely yourself. So, for example, we had a failure in CDU 1, right? And now CDU 2 is part of this group with CDU 0, right? We can create a new group. We can do all sorts of things. There are unions. There are all the group type operations that you would expect for building rich and unique groups here as well. And so we're really using a lot of this grouping functionality to create logical groupings as well as use our system as a whole, combined with our new objects that are CDUs. Now you might ask me, what if all the CDUs don't look like the same thing? What if they're not all serving multiple racks, or they're, half row CDUs, or everything isn't just an in-rack CDU, or a CDU combines with rear door chillers and other types of CDUs throughout my system? And the answer is we can support those as well. So let's get into the different idea of cooling domains. So we can think about a cooling domain here as something where we have a facility BMS, right, to track all of our system level CDU items. And I should give credit to Chris DePrater for creating this diagram, what we've used in the working group quite a bit. And then we have items where CDUs are tracking requests and passing them back to facility BMSs. So we have CDUs that are built in. And then we have the idea of a cooling domain that's underneath a CDU, which may be several racks and maybe portion of a rack, right? So each node here is giving requests back to a CDU on power through the PowerAPI. So all of these computing components can be reporting their powers back to the CDUs. The CDUs themselves can be using PowerAPI to then set conditions or report conditions back to a BMS. So what's happening here is the PowerAPI is useful not only for the user, it can also be used to write some of the software underneath, such that a rack can be ambivalent to the type of CDU that it is communicating with, because it can use PowerAPI as a whole. Okay, so let's take a look at a new example of a PowerAPI system of objects with floating cooling objects in them. And I should mention an important point in here. Part of the reason why we use this layout for the PowerAPI is that it is very compatible with existing tools that will already map systems in this way. So if we take a look at tools like HWLope, they will map out systems in these similar ways and can be augmented on top. So we're leveraging existing tool sets here, as well as existing practice in navigating through systems in these ways. So let's step through this hierarchy. And I should mention that these things aren't fully ratified within the Power API yet. So there are still options to be able to come in, give us feedback, and contribute to these ideas as well, especially with regards to our metadata that we're still finalizing. So overall, we have an object, the facility, right? We have a couple of platforms in these facilities. There's a platform 1 over here. Let's just ignore it for now. We don't need platform 1. It exists, but we don't need to know. There's more stuff underneath it. So when we come down to platform 0, we could have something like cooling group here. Here's a cooling group. CDU 0 services rack 0 and rack 1. Rack 1 has some chassis. Rack 0 has some chassis and some other stuff. Let's ignore that for now. Let's go look at rack 1. Rack 1 has some chassis, but look, it also has a CDU type, CDU. And this is a different type. For example, rack 1 may be serviced by a larger CDU, but it may have something either within the rack itself, which is servicing multiple different chassis, so further CDU disaggregation here. Or it could be, for example, a rear door chiller that's also happening in this rack, right? This chassis has boards. Those boards have nodes. Those nodes have sockets. Things like network interfaces also float around in this system because they can be attached to things that might be attached to an individual socket, or they might be attached above a socket on a PCIe from a PCIe perspective, or other interconnections perspective. So this entire diagram, everything you see here that's an object that's in orange, is a floatable object in this hierarchy. I've not included GPUs and a whole bunch of other things in here because it gets way too cluttered way too quickly. But you can see how we can support multiple CDUs, multiple different types of cooling groups, and multiple CDU types in a single hierarchy, in a single object description of the system, and including multiple different cooling groups as well. So I only put one cooling group in here, but there can be many, many of them, and they can overlap as well. So in summary, what we've been doing in Power API, we've been adding new objects, attributes, metadata, groups for the Power API for liquid cooling. Been working on the flexible placement of objects, which is a concept we already had in the API, but we're making sure that it works well for all of our cooling elements. Grouping convenience and customizability is a big concern for us. You can do what you need to do programmatically with these systems. So you can monitor and control all the liquid cooling in your system in a portable way, regardless of what vendor support you have inside your system. As long as you have some basics to be able to do some programmatically possible items, we can support it through a plugin interface. Whether or not we have the plugin, it's just a matter of adding a new plugin if we don't have it. And then we want to understand system and interdependencies here, so we can also deal with larger systems that have redundancies and failures as a whole. And so I want to call everybody to please come join us. There's still opportunity to have impact here. Our next meeting happens to be Friday, May 3rd at 9 a.m. Pacific. If you can join us, we'd love to have you. If you want the details on how to join that group and get signed up for the mailing list, you can visit the EHPC WG working group website. In the calendar. You can also find links to everything I've discussed today, including multiple implementations of Power API, the spec itself that is open, and our reference implementation at powerapi.github.io. And if you'd like to see the specific cooling controls work on the specification, that is the specific branch that we're doing everything on. It's all open, and we welcome feedback from anyone, and we welcome you to our meetings as well. And with that, I think it's time for questions, Natalie.
Thank you. All right. Okay, why don't we start with questions and just alternate? So Ryan, why don't you take a question and then turn it over to Jeff, and we'll see how many we get through. There's a whole bunch of them in the chat.
Figure out okay, I'll take the first one down at the bottom. No, that is not the website for the Power API. So after we debuted the Power API, there was a Power API that came out that's meant for commercial products like refrigerators. That is not it. So please go to our github.io website. That's the official one for Power API. You can also go to powerapi.sandia.gov, and it has a pointer to there as well. All of this originally started at Sandia with Jim Laros. And so we still have a link to that on the Sandia National Laboratories government website And you can consider that a fairly official way to get information about the community as a whole as well. Although that really only points to the community items itself. So let me look through the list, Natalie, and then we'll take the next question. We'll pass it along to Jeff.
Okay, Jeff, go ahead. Take a question.
Yeah, so I think I've been answering some of them in the background, but I think one of the things that that came up was a question about, is there recommendations for how do you access the interfaces through particular admin nodes or whatnot? And I should have mentioned that so the Redfish pieces were intended to be directly surfaced by the cooling units themselves. As all the data center infrastructure components are kind of going through this, once in a decade, transition to web-based interfaces. One of the keys for Redfish was to leverage what folks were going to be doing anyway. So anyone building a web GUI means that you already have HTTP, you have Ethernet, you have all of the relevant security pieces to do a web interface. And gee, if you're doing a web GUI, you also need a communication mechanism to go between your front end and your back end from the browser to the system itself. And so, you can use Redfish for populating your GUI at the same time as you provide an out-of-band API. So the answer there is, while you can surface Redfish information in band, for a CDU, don't believe that connectivity is normally there. So instead of trying to force that into an in-band piece, we're expecting that the cooling units at some point are going to have a controller with an Ethernet jack, and so that's the pathway. And Ryan, other questions on there? I think now I think folks have been asking for website links and whatnot, so I think we'll gather those up and provide those. I think Natalie, you can do a summary email with all that information, so we're not losing it in the chat.
Sure.
Yeah, the most common question that I get when we do these presentations, Jeff, and I think you too, is just the interconnection between the Power API and Redfish. And I would just say we're friends, right?
Yeah.
We're trying to do complementary things here with each other. So this is not a competition type thing. We support Redfish, like abstraction of things underneath Redfish. Redfish tries to do things with hardware support that we do not dictate. We are a software layer at Power API. So you'll even see that a lot of our attributes and things are very closely aligned in their definitions, so that you can be confident that assumptions that you're making within a Redfish situation align well with a lot of the time with our metadata, so you can understand fairly quickly whether or not your expectations in those types of systems are being met, or whether you have other hardware that is not Redfish compliant as well inside of those environments.
Yeah, very well said, Ryan. I think dovetailing more than smashing is is I think our way of describing it. And we see areas where there's we want to make sure that there's coverage in both places. So it's as things show up in one model, you'll see and hopefully we try to use some of the industry terminology as well, so that we're not defining things in conflict.
Well, if you guys think we've covered all the questions that are in the chat, we do have 2 minutes left. Is there anybody, who of the participants who want to ask a question with their voice instead of the chat? Okay, well then, Ryan and Jeff, thank you very much. That was well done. You guys were very thorough, provided a great overview as well as a lot of depth. And we had a lot of participants. Thank you all for coming. And I hope that everybody continues to participate in this effort by getting involved with some of the team activities that both Jeff and Ryan have going on. And if you have any general questions about the EEHPC working group, always feel free to contact me. All right. I think we're done. Thank you very much.
Right. Thank you, Natalie, for putting this together.
Thanks, Natalie, for hosting. Thanks, everybody, for attending.
Bye-bye.